Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. Still arguing with these people. Okay, what the hell. So Ian Gosling hasn't made a video in 7 months. I thought it's because he was being sensible and saying, you know what, this really is mushy physics, and I probably should just stay the hell out of it until I can actually say something with any kind of confidence and rigor, because he had made a lot of errors, and so I thought he was being a little more cautious. But so he makes this video, which is again just so simply stupid, frankly, and I really shouldn't. This shouldn't be my job, right? I mean, I shouldn't be the only one to point it out to him, and I will be the only one to point it out to him. You're just missing the whole understanding the concept here. So they're obsessed with the fact that they can make balances move at somehow different speeds, and they're saying that proves when, well, obviously it doesn't prove anything, in the sense that you have to calculate the actual momentum being generated by the lever. You're putting a certain consistent force in, and if you actually have the objects where they have to acquire more momentum and you're using the same force to create that momentum, of course they're going to move slower. But what won't happen is if you keep the ratio of weight exactly the same. That is, you put a 2 mass at one distance, and then you put a 1 mass at 2 distances, and then you put a half mass at 4 distances, then you'll be okay, because it's the same momentum. But you can't make comparisons between a system that has a total of, say, 2 momentum and then have a system that has 4 momentum and then say, look, they move at a different speed. Well, of course they move at a different speed, because it's twice as much momentum you're creating with the same force. So obviously everything moves half as fast, because it's twice as much momentum required to move the objects at the same rate as before. Alright, so it's just, I'll draw it because it needs to be drawn, frankly. So he's created a lever. Now a key point is that the fulcrum he's made is a big hole in the stick, so the stick is actually riding on the top, so it's essentially the same as a balance suspended from above, so it will oscillate. So if he made a small tiny fulcrum in the middle, it wouldn't be able to oscillate, and certainly if he supported it from below, it wouldn't oscillate. The reason why it's oscillating is because, yes, he's bored a big hole, and the stick is actually being suspended from the wood on the very top. Just pointing it out, that's another feature here, is you have to understand what kind of lever you have. And the reason why a lever oscillates is because it's switching matter from one side to the other side, because of the fact you've suspended it above its center of mass. So if you suspend it, if the fulcrum is above the center of mass, it will oscillate. And it only oscillates because you're putting in a little bit of matter switching sides. And so obviously you have a small force is creating the motion, and if that small force has to move more mass, then it's not going to balance. Now you can just do this with a spinning disc, and maybe I'll use that as an analogy, because the same rules apply. Rotational momentum is the same as linear momentum. Same rules apply. Alright, so I'll just play this part. So he sets it up. He's got a metrodome, and he says, look, I have the weights here and here, and then he takes the same exact weights and puts them here and here. Now you need twice as much energy to move the system. So he essentially moved the weights, a 1 mass and a 2 mass, okay, and he just proportionally moved them further out, so he doubled their weight. So now they require twice as much energy to move, is the obvious answer to his question. But let's just let him say the damn question.
Now why, if it's a balance.
So being a balance isn't the rule. The rule is how much momentum, total momentum, do you have on your oscillator?
Is the frequency change dramatically on this?
Because it's twice as much, technically it's twice as much weight that has to be moved with the same force.
Much slower now, isn't it?
So we'll
That's
see
a question for Gary of Draft Science. I'm sure you've got plenty of ideas why.
Yeah, it's obvious why. And again, so I don't even know why this is an issue. Like I said, first, the very fact that you think you're proving the lighter mass can't be moved at twice the velocity with the same force because there's a tiny difference in the oscillating rate is silly, frankly. Okay? And the fact that you're going to deny, like I said, he's kind of an engineering guy. Look, he's got a workshop full of stuff. He knows this stuff works. He knows that you can balance a wheel. He knows that you can put a small mass at the high location, increase the momentum, and that it's going to balance the other weight. So he knows that these rules apply. He knows the law of the lever works. So why is he defending an argument that's saying it doesn't? It's just so ridiculously stupid. This is like him defending it takes 25 times the fuel to go 5 times as fast. It takes 25 times the electricity to spin your drill 5 times faster. Bullshit, it does. And yet he's defending this nonsense. You're just like, why the fuck are you doing this? What has you so confident? Because some nerd told you so? Some nerdy scientist told you so? And that's why you believe?
Probably start with the first one that I've cheated on the weights or something ridiculous like that. Anyway, assuming that I haven't cheated in any way.
So again, all this premise of this is a miraculous... No, this is not. This is totally predictable. This is not miraculous. This does not prove anything because you doubled how much work has to be done. And you didn't double the force you put in. So obviously it takes twice the amount of energy. If you want to go this, if you want it to go the same speed, you'd have to put in twice as much energy somehow. And because you're using gravity, you don't have any way to put twice as much energy in without artificially creating some sort of mechanism. But you just don't get it. You move the weights twice as far out. You've doubled how heavy, okay, from the force's point of view. What work the force has to do. You've doubled the work the force has to do. And if you would have reduced the weights by a half and put them twice the distance, that would have worked. Then it would have oscillated at the same speed.
And this would be repeated thousands of times by different people.
So again, this lie that they've done this experiment, that they've proven anything. I mean, just overtly lie in your videos. Okay, then yeah, you're just going to piss me off. I'm sick of liars. I mean, what a pile of crap. Link me to this proven experiment, you fucking liar. God damn it.
Would be your answer for why this is happening. I like these mechanical metronomes. No
Well, whatever. I don't have any use for it. Frankly, it's just irritating.
batteries required.
So this was should have been a 17-second video. Actually, the 4 minutes was a waste of time. All right. So anyway, just so bad. All right. So here's the simple physics to understand. As I have pointed out repeatedly, I mean, I've done this over and over and over again. Oh, I have to fix the focus. Should be back. All right. So lever. Where's my pen? Oh, jeez, frame rate sucks. Okay, I'll be back. Fix that. Alright, should be working properly now. Alright, so I've repeatedly pointed out that there's physics, science to how a lever functions. So I'll draw it very thick to make the point. And the simple argument is you can have a fulcrum here, and here in the middle, okay, or here underneath. You know, you could have it above, middle, or below. And each one will behave differently. So if you have it below, you're really in trouble in terms of being able to get it to oscillate or anything like that. Because as soon as there's a tiny bit of extra weight on one side, the lever itself, as it moves, okay, it's going to move on this fulcrum. So you can understand if this side goes down, it's going to essentially, this line is going to go moving over. So this much mass is going to be added to this side. So you can understand that when it tilts, it's going to go like that. So all the mass on this side went over this side. So the side that was a little tiny bit heavier now is even heavier. So you're going to just get all down or all jerking this way, but you're not going to be able to get it to oscillate. You might be able to get it to balance by working at it, holding it, being really careful, but it won't oscillate. Now you can get a little bit from the center, but the center basically does is it just says it's always equal. So you don't gain any extra mass. So no matter how it rotates, there's no line I can draw to say, look, the line changed and there's more mass on that side. There's always the same amount of mass being put this way as that way. So it's always, you know, I could put an X here and you'd get it that, you know, no matter which way I turn it, the extra mass I'm putting on one side of the lever is always compensated because I put the same amount on the other side. I just changed where the center is. So there's more here at the bottom and more here on the top. So I've got the same amount of weight on both sides. So you can move it to any position and it'll stay in that position. So it won't oscillate. Now what he did was drill a big hole. So essentially the lever is riding on the top. And if it's riding on the top, it's going to do exactly the opposite of this, okay, which is the line is going to go in exactly the opposite direction. So as this side goes down, what's going to happen to that line is it's going to be taking mass away from that side and putting it on the other side. And so I would draw that as, well, essentially it's got to be a line going this way. So when this side goes down, that is, if this side gets heavier for some reason, the fact is the further it tilts, the more mass went on to the other side. So it's always compensating. So that's why you get it to be an oscillator. All right. So that's the real science of the lever. So first off, you have to deal with that being an argument that you're just ignoring, pretending it doesn't exist. So that's the thing that's moving in the lever. When the lever's oscillating, all it's doing is switching that little bit of matter side to side, side to side. So when it's oscillating, there's only a tiny amount of force that's actually moving the lever. Fact. And it's not, it's essentially not moving the masses. The masses are staying the same, their momentum is staying the same, and what's changing is the tiny bit of friction in the system, and that's the only thing that's going to degrade the oscillator. All right, so let's deal with his argument, and I'll just lightly explain what's wrong with it. All right, so what he did was he's got his fulcrum above. All right, so it will oscillate. He's got a 2 mass, presumably, and a 1 mass 2 distances. And what he's basically saying is, look, I'm going to move those twice as far out. So he's going to take the 2 mass, move it to 4. Okay, and he's going to take the 1 mass and move it to, well, whatever, the extra 4 distances. So it was 2, it's going to be 4. This was 1, it's going to be 2. Now you can understand that what would be the momentum if it moved at exactly the same speed as this. So in this arrangement, the total mass is 3, you could argue, and in this arrangement it's 4 plus 2, so it's 6. It's twice as much. So essentially you need twice as much momentum to move this, you would need twice as much momentum to move the 6 pounds as you need to move the 3 pounds, obviously. So 6 pounds is going to take more energy to move. But the lever is the same lever. They're still just the same mass switching sides. So you have the same moving force, and now you're moving twice as much weight. So the way to really do the experiment, the argument I'm making is that you can't change the inertia. Okay, it will be exactly the same as long as you keep the total amount of momentum required to move the object the same. So I could, let's just do this, and we'll do it with the 4 mass just to make it so we can have plenty of flexibility. So if I had have the lever and I put a 4 mass here, okay, so I have 1 unit of distance and I put a 4 mass. All right, now we're just saying what equals that. Well, we know that at 1 unit of distance I could put a 4 mass. All right, at 2 units of distance, oh Jesus, 4. Okay, at 2 units of distance I could put a 2 mass. All right, or at 4 units of distance I could put a 1 mass. So we know that will work. So my argument is that whatever this oscillates at, so you put a 4 and a 4 and you get an oscillating speed, it'll be the same as the oscillating speed for the 4 and the 2, and then it'll be the same as the oscillating speed for the 4 and the 1. They'll all oscillate at exactly the same speed. And the point I was making is that if it fails to do so, say you have the 4 to 1, you have these two, and it oscillates at a different speed than the 4 to 4. Well, I'm simply going to make the argument that you have this actually in the wrong position. So measuring the position is fine, but you have to understand that you're not measuring it including the weight of the lever. So the weight of the lever is going to steal some of the capacity of the lever to make the conversion. It's diluting the ratios. You have to really say the weight of the 4 pounds plus the weight of the lever. So you have 4 plus weight x, and then you have 1, okay, times the 4 distance, so times 4 times, okay, the weight of the lever, weight of x. So you have to, well, it's plus actually, not times. So you have to recognize that you have diluted the weights by the weight of the lever. So the ratios aren't perfectly 2 to 2, the distances aren't going to be perfect. So obviously with the 4 pound, it's going to be even. But as soon as you're creating some asymmetry, now the weight of the lever matters. And so this mark, instead of being exactly twice the distance, might be right here. So if you put the weight right there, it will oscillate at exactly the same speed. And this one might be a little bit more off, so you have to put the weight here instead, the 1 mass. And then it will oscillate at the same speed. So that's how you are cheating the experiment. Is because you're not recognizing first that the force in, okay, is consistent in the sense that the force moving the lever is just the change in the gravitational mass of the lever itself. This side gets heavy, then this side gets heavy, then this side, and it just keeps switching back and forth. So as the lever goes down, this side gets heavier, so it obviously gets forced back down again, so it overshoots. Then this side goes up, it gets heavier, it goes down, and that's what's moving the lever. So you'll have a fixed force of gravity affecting a portion of the lever. That's your force in. And the simple truth is that, yes, at 4 to 1, if you get these distances correct, that is, it'll be a little bit nuanced. You can't use the idealization because it's not an ideal lever. It's not a massless lever. So the fact that the lever has some mass and it's consuming some of the, you have to move the whole lever, including the weights, that's going to change it just a little tiny bit, and you just make a small adjustment in where you place the weight and you will get the same oscillating speed. That's my argument. All right, so argue my actual argument, not some fake straw man that you've created where I said somewhere that, well, if I put a 4 pounds out here, if I change the experiment, right? In this experiment, you have the same weight, the same momentum weight in each case, right? You have 8 here, then you have 2 times 2, 4, so you have 8 there, and then you have 1 times 4 plus 4, you have 8. It's always 8. What you did was you put 4 out here, created 4 times 2 times 4, and then on the other side, created another 16. So it's 2 different experiments, and you could figure it out if you put it on a wheel. You can understand that yes, if I had put a 2 mass here and a 2 mass here, I'm going to have a certain amount of momentum I'm going to be generating by giving the wheel a push. But if I put the 2 masses out here, we know that they're going to have twice the momentum. So now I'm going to need twice the energy to move the wheel at the same speed if it was an ideal weightless wheel. And again, we could understand that if we had to include the weight of the wheel, we know that this distance rule isn't going to work. I can't use explicitly 1 unit of distance and 2 units of distance if I don't account for the fact that the wheel has a mass. So if the wheel has a mass, I have to include that in my calculation of where the exact location of the twice the distance should actually be, because it's not an idealization. All right. So maybe we'll read some comments. I saw a comment on Dispar's video that he's supposed to be doing the video with an actual pendulum this time, the lever launcher. But we know it's going to be a piece of crap. So I just don't have the guts yet to go there, but we'll see. Because this is all the game they're playing is it's Gary's job to figure out how they cheat. Okay, so in this case, the cheat is a straw man, because I never made any such argument that twice the mass doesn't take twice the energy to move the same speed. If you're going to move twice the mass, the same speed, you're going to have to produce twice the input force. And lifting something in gravity and letting it go is not going to be twice the force, because what you've really lifted is just a tiny bit of the lever. So unless you're pushing and creating an active force that you can double, then there's no point in putting twice the weight essentially on the lever and telling me it should move the same speed, because no, it shouldn't move the same speed. If you're generating twice the momentum, you need twice the force to do it. That's going back to Newton again. All right, so let's get rid of... Well, I have to figure out where the comments are. Kind of strange that he's got such a wide format video now, so he must have got some different camera. Very wide. Anyway, okay, so yeah, lots of parallax now. Even more parallax fun. Alright, so let's see what the moron Dispar says. Nice to see another video after all these months, Ian. Also nice that I've inspired you. So that's the sad, tragic part. I also have one more of these antique metrodomes. Good idea to use as a reference balance. So again, for a point they're never going to be able to prove, which is somehow the half mass doesn't move twice the velocity, when the balanced lever proves it does, because the 4 mass, I mean, I showed it. It works just fine. But anyway, Gary misunderstood me when I said place different mass ratios at different distances from the fulcrum. Yeah, well, I don't know how you can misunderstand that, frankly. His famous porch balance lever only showed a 1 mass versus 4 mass. Yeah, so why should I mean, I could slide it easy enough. I could put a 2 mass and could have showed it. But what would I be proving? All right, anyway. but he never compared that with a 1 mass versus a 2, for example. And again, as long as the 2 mass is in the same location, that is, you just moved a 4 mass over 1 and reduced its mass by half, it's exactly the same momentum in the system. If I put it on a wheel, the wheel will spin exactly the same speed. The wheel cannot tell the difference between the 4 mass in close, the 2 mass 1 unit of distance, and the 1 mass 2 units of distance. It can't tell the difference. Well, 4 units for the 1 mass, 2 units for the half, the 2 mass, and 1 distance for the 4 mass. For example, to see whether or not they oscillate the same way. So again, and they should according to him. Yeah, and the own video you published basically showed it. So I showed the clip where the stopwatch was wrong, and I put the 2 videos right on top of each other, and you could see they were moving at the same speed. He only uses the 1 to 4 and says here's it balances. I'm just proving that the 1 equals the 4. I don't have to. I'm not doing a comparison between a 2 mass and a 4 mass and a 5 mass and a 6 mass and any of that other crap. I don't see the relevance. You're the one who thinks it's relevant, not me. All right. If he chooses to watch this video, he will definitely. So again, all right. I watched the video and it's again garbage. All right. It's a garbage assertion that has nothing to do with anything I have argued. It's completely. Again, I could have predicted if he would have told me ahead of time what he was going to do. I could have explained how, well, you're changing how much mass you're moving. So obviously it oscillates at a different speed. You've got the same force in, and you've got twice as much mass to move. That isn't going to work. Of course, it's not going the same velocity. All right. Don't get sucked in again in his endless loop to the point that it makes you blood boil. So again, his blood is going to boil because he straw manned the argument and he's too fucking dumb, even though I've explained it 17,000 times how the motherfucking thing works, in the sense that you're just shifting the mass of the lever. There's no extra force you can capitalize on. All right. If he chooses, okay, I did that part. I hope you're doing well. What an asshole. What a fucking asshole. Anyway, so that Falwell moron says, nice to see you back. Hope you're doing well. Oh, this good to use audio. Good use of the audio and visual. So it's actually a very poor use. Okay. As Dispar just pointed out, don't get sucked in by him by trying to wind you up again. So again, I'm winding him up by making physics arguments where I actually explain why I believe what I believe, and they explain nothing. I mean, absolutely. So, yeah, let me just draw it. I mean, let me just ask the question. I mean, why do you believe this crap, this stupid, moronic, idiotic theory? All right, if you had to draw it, you can't make it make any goddamn sense. Let's see, will that work? Yeah, that worked well enough. All right, I'll pause to erase. All right, so, I keep asking these people. I asked Paul Nord, I mean, come on, please just tell me, why are you so confident? What experiment makes it so obvious to you that somehow there's something magical, okay, in me doing this to a circumstance? So let's say I have 4 things, 1 mass objects, okay, and they're moving 10 velocity, okay, and they're going to now exchange their energy with something, right? Or I could have, 2 of them. Yeah, my bad. 2 of them, all right, moving 5 velocity, right? And these are double masses, right? Well, I guess they would move the same. Okay, so I've doubled the mass and I have the same velocity, 10. All right. So it's the same mass, and all I've done is put it in bigger objects. Now, so they get that that's the same. And so the simple argument is that, so you're saying, though, is if I have 4 and then I take, the third choice, which is I just take 2 and I make them go 20 V, that somehow I don't have the same energy. That somehow this, doesn't add up to the same capacity to exchange it and make something else move, and that's all we're talking about. And so we're back to like the bowling ball example. I mean, what do you think happens when something hits something? If the bowling ball hits at the first pin, and okay, so it's the 8-pound going 16, what's the pin going to do? Well, the pin's going to leave at 16 as a maximum, and the ball's going to lose, okay, whatever the weight is of the pin. Let's say it's 3. Well, then it's 3 times 16, all right? And so that's how much the bowling ball is going to lose of its momentum. So you can understand that, okay, so when the 16-pound ball hits, and it's only going 8, and it's only going to move the pin at 8 miles an hour, so it's the same 3-pound pin. It's only going 8 miles an hour this time when it leaves. So I've lost half the amount of energy per that impact. So the big heavy ball lost less. So this one's going to lose its energy rapidly, okay, and this one is going to lose its energy slowly. And so all you're going to end up with is those two lines are going to cross. And this is going to be the same as this, okay? They're both going to end up transferring the same momentum because that's all they have. They don't have any kinetic energy nonsense. They don't have anything but their momentum. I mean, how can you believe there's some other mechanism? I just don't see it anywhere in the universe. Why do you believe this crap? They tell you, I mean, again, you really believe I spin a water wheel 5 times faster, it can do 25 times the work now. I spin a turbine in a dam, and I spin it. I create a funnel for the water, so the water's going faster, and even that won't do it. I mean, you can't make the wheel turn any. I mean, you have to add more momentum. The speed of the water is not going to help you any, because the force, you still have to apply a substantial force to actually move the wheel. All right, so just get rid of the blue screen, okay, and finish this crap. Okay, so then this is the John Sean Walker kook. So he says, great to have you back. So he did a garbage experiment. He calls it a nice experiment, proving absolutely nothing, straw manning the whole subject, just absolute useless crap. He didn't counter any argument I have made. The probe in the second setup is roughly the same velocity as the first. The probe? What's a probe? Where was it a probe? But the probe travels twice the distance per oscillation now. So obviously, the point is the lever's moving the same, but it has to move slower. I mean, it's the same distance, but it has to move half the velocity because there's twice the weight on it. Twice the weight from the fulcrum's point of view. You have a good one, dude. Oh, God. So then Brozo shows up to say, nice one, Ian. So it's a garbage video straw manning the argument. Hard to see what his objection could be. I mean, it's so obvious. Okay, so none of them are smart enough. They really don't know how any of this shit works. And that's what just makes this whole thing such a waste of time arguing with these people. They pay no attention to any mechanical function. They will not learn any of the mechanics. But we know there will be one. Yeah, obviously. Because it's a silly theory. Again, I can't believe these people they're arguing that the law of the lever doesn't work. And they don't know how significantly a stupid a thing to say that is. In the sense that gears and levers and pulleys and all this stuff are famous for being conservative of energy. Old metric bones, okay, so I don't know, the thing to look at, the modern beep, 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 okay, who cares? Alright, so maybe I'll just leave it there. Why go look for more trouble? They're just junk. This is just such garbage to have to put up with this shit. Oh yes, another one of your great debunks. Completely off the subject, essentially. Proving absolutely nothing, demonstrating absolutely nothing. Just more fake, phony, fraud physics by these lying trolls. Ugh. Shit. I wish there was a real adversary to argue with. but they all run away. You know, all the ones that have credentials. I still can't get over that. Like I said, the Paul Nord. I mean, for him to argue the law of the lever doesn't apply is just so ridiculously stupid. Oh, yeah, just I can't. What are you gonna do? This is the planet I'm stuck on. Assholes, fucking trolls and assholes. Nothing else.